Hello and welcome to SETI Live. I'm your host, Beth Johnson, Communications Specialist here at the SETI Institute. Welcome to all of our viewers joining us from around the world. Thank you for being here. Please let us know where you are watching from. Welcome to our listeners on the podcast version of SETI Live, available on most podcast platforms. And welcome into the viewers who are watching this at a later time. Thank you for taking the time out of your day to do so. All right, life is full of surprises, but this one's a little wild. Imagine a microbe that doesn't have to choose between oxygen or sulfur to survive. It just uses both. Today, we're diving into how that works, what it means for life on Earth, and how it could guide our search for life elsewhere. I am excited to be joined by Dr. Eric Boyd from Montana State University, a microbial geochemist studying life in extreme environments and the lead author of a recent paper in Nature Communications, which reveals that a newly discovered bacterium can thrive in environments where oxygen and sulfur coexist, using both to fuel its energy production. So thank you for joining me, Dr. Boyd. Welcome into SETI Live.
Well, thank you, Beth.
So can you how does this, just give me a brief how microbes use oxygen and sulfur primer to sort of set us up for this. I am not a microbiologist. I'm not even going to pretend to be a microbiologist. So I'm going to let you do the microbiology part.
Sure. Well, take a deep breath, everybody. And you just breathe in 21% oxygen. And essentially, that's how you're burning your breakfast, lunch, or dinner that you ate. And you're burning that organic carbon and coupling it with the reduction of oxygen to release energy. And that's a common form of metabolism. What's less common is our metabolisms that don't involve oxygen. And so imagine a microbe that instead of breathing oxygen, it breathes elemental sulfur, a yellow mineral. And those organisms exist, and we've known they exist for a long time. What we didn't know existed were organisms that can do both of those things at the same time. They breathe oxygen while at the same time they're breathing elemental sulfur. And that's really the profound discovery that we report in this paper.
I'm utterly fascinated by this. I've been sort of fascinated by extremophiles since I learned about astrobiology as a concept and really started getting into, this is even prior to when I was finishing up my degrees, but just the wide variety of places where we have managed to find life here on Earth is astounding to me, and finding out that it exists in these hot sulfur ponds and springs was unreal. And I've been to a couple and gotten to see sort of, realizing that the colors on those are actually all of this microbial life. And that is just an amazing experience. If anybody has a chance to go see some of those, that is incredible. So you did this particular research at Yellowstone. You seem to do, you're at Montana State, so obviously you're going to do a lot of your research at Yellowstone. What exactly did your team find and where for these Yellowstone microbes that we're talking about today?
Sure. And so Montana State University here in Bozeman, Montana, I can be at my field site in Yellowstone in 2 hours. And so we have this advantage over researchers at other universities. And so there are a plethora, there's a long history of thermophile research at Montana State University, and that continues to this day. One of the things that has always fascinated me about hot springs and the microbial life that lives in hot springs is the fact that there's just a limited amount of oxygen. And so something that you may not know is that the solubility of oxygen in water decreases inversely with the temperature of the water. So high temperature fluids or waters don't have a whole lot of soluble oxygen. This is one of the reasons why when it gets really hot, fish have a hard time breathing because there's less oxygen in solution. Well, now that's at 20 degrees centigrade, 70, 75 degrees Fahrenheit. Think about that when you get up to the temperatures of boiling. We find these microorganisms thrive in these conditions of really low oxygen. And there's other minerals present, like what you mentioned, these sulfur-rich springs. And so it just really started to raise the question, if oxygen is low in availability and it fluctuates with the conditions in these hydrothermal systems, how is it possible that these organisms thrive in the ways that they do? And that's kind of what stimulated the research that we describe in this recent paper.
So why did scientists used to think that you couldn't have this two-way, this both ways thing? You couldn't have it both ways. Why was that? Why did scientists think that?
Yeah, it's a great question. And so the textbooks will tell you that. And the textbooks, the microbiology or the microbial geochemistry textbooks, present this concept of the redox tower. And what I mean by that in simple terms is that you can maximize the amount of energy available in, say, a banana by oxidizing it with oxygen. And the next most might be with oxidizing it with iron, breathing iron. And the next most might be with nitrate. And the next most with sulfur. And so an organism, because they're under selection and they're competing with each other, they're going to try to maximize the amount of energy that they can get by consuming those electropositive, the better oxidants, if you will, oxygen, for example. So that's one reason. And so an organism should have to choose what it's doing. It can't do more than one thing at the same time. So that was one concept that the textbooks teach you. The other is that a lot of biochemistry, a lot of the enzymes that actually allow for anaerobic respiration don't function in the presence of oxygen. Oxygen toxifies those enzymes. And that makes sense because a lot of these enzymes evolved on Earth before there was oxygen around. And then they just had to simply deal with the fact that oxygen was there. And so what they do is they turn off their anaerobic parts of their metabolism when oxygen is present to take advantage of that better oxidant, and then turn that anaerobic part of the respiration back on when oxygen is absent. So those are the kind of paradigms that existed and that we were confronted with when we started conducting this research.
All right, I want to talk to you more about that, but I'm going to welcome people in from where they're viewing. Let's see, we have people joining us from Sweden, North Carolina, Mercer Island, New Jersey, England, Idaho, that's close to you, Illinois, California, welcome, sunny California, it is, kind of, Washington State, Czechia, yeah, wow, okay, so, and Germany, so an awesome range of people watching, and from Mexico, thank you. So thank you everybody for joining us. We're talking about the discovery of a microbe that can breathe both oxygen and sulfur at the same time. Okay, well, how did you and your team first realize something strange was happening with these microbes?
Another good question. So we simply asked that same question. Can this organism take? So essentially we had an oxygen probe. So we can measure really accurate low concentrations of oxygen. So we isolated this organism, and the organism's name is Hydrogenobacter, for those that are interested. It's a early evolving member of the Aquaficales, for those taxonomists that are out there. But a bacterial organism. We'd isolated it, and it would grow extremely well with oxygen. We'd feed it hydrogen gas and oxygen. And so this is how NASA launches stuff into space, by burning hydrogen gas with oxygen. Well, it turns out there's microbes that do that to fuel their own metabolism. So it grew extremely well under those conditions. And we'd go to the environment with our oxygen probe and we could almost never measure oxygen. We're like, okay, well, that doesn't make sense. This organism's abundant in that hot spring, but there's not a whole lot of oxygen. Well, we sequenced the genome of this organism, and we found that, well, it looks like it can also breathe elemental sulfur, the mineral. And so we set up experiments growing with hydrogen and elemental sulfur in place of oxygen. And the strain metabolized great. It made hydrogen sulfide, a product of sulfur reduction, but it didn't seem to grow. And so we're like, huh. So it can generate energy from that process, but it can't couple it to growth. And that didn't make any sense to us. Why would an organism hold on to the gene repertoire and the enzymes to metabolize elemental sulfur if there's no real gain? And so we just set up that experiment and asked, okay, well, maybe, outlandish as it sounded, maybe these organisms actually benefit by respiring elemental sulfur at the same time as they respire oxygen. And maybe that's how they survive this really low oxygen concentration in their natural environment. And sure enough, they did.
Wow. Okay. So tell us about this environment. What is so special about the Yellowstone environment? So you were saying that you measured that there wasn't a lot of oxygen. So specifically, what were the pools that you were looking at?
Well, the specific hot spring that we isolated this organism in, there's really nothing extraordinary about that spring. It's one of many that are similar to it across Yellowstone. There's 10,000 hot springs, fumaroles, geysers in Yellowstone. It's the largest concentration of thermal features in the world. So it's not surprising that it's hard to find one that's truly unique among those 10,000. But it was called Roadside Springs, and specifically we call it Roadside West because it's west of another spring that we call Roadside East. But moderately acidic, pH is about 6.5. The temperature is actually not terribly high. It's about 75 degrees, 80 degrees in some places. But what's unique about the spring is there's a ton of sulfur in it. And that's not common to find in a spring that's pH 6.5. And the reasons for that get too complicated probably for most people in this audience, but nonetheless, it results in a chemical condition where oxygen, there's this huge sink for oxygen, a chemical sink for oxygen. And so you have this combination of a chemical sink for oxygen, and you have low ingassing of atmospheric oxygen because of the high temperature. And so it creates this situation for the organism where they have to compete under those conditions. And so again, nothing terribly unique about it other than the fact that it was hot, really hot, and it had a lot of sulfur in it.
So just, a hot spring. For those of you wondering. All right. And how do these bacteria switch or balance between using oxygen and sulfur?
It's a concentration effect. If we maximize the amount if we give the organisms maximal amounts of oxygen, we don't see this phenomenon. It's only at low concentrations of oxygen. So there's some genetic switch inside of that cell that says, okay, oops, there's enough oxygen here. I'm just going to burn all the hydrogen gas with oxygen. But when you get to really low concentrations of oxygen, that's when they start to allow that secondary metabolism, that sulfur respiration to happen as well. And so exactly what the regulatory switch is inside the cells, we don't yet know. It's something that we're interested in following up on, but we don't exactly know how the cells do that. But it does make sense that the cells would do that, because if the concentration of oxygen inside of the cell gets too high, those enzymes that are involved in respiring elemental sulfur, they're going to be toxified, and they're essentially going to denature and not be functional anymore. So it would make sense for the cell to not invest in the synthesis of those proteins until the concentration of oxygen gets low enough where those proteins can still function.
And were you expecting this kind of result, or was it a total surprise? It sounds like it was kind of a surprise, since it was. So I feel like this is one of those cases of yes, you find it in the last place you look because then you stop looking. But did you really feel like you had run out of your options of understanding what was going on here until you hit this?
Let's put it this way. I never closed the book on anything as being possible. And so one of the things that my research advisor when I was getting my PhD told me is, as soon as somebody tells you that something can't happen or something can't exist, that's when you start looking for it.
Right.
And so you're always trying, as scientists, I mean, this is what we should be doing, is we should be looking for the extraordinary, not the ordinary. Mm-hmm. And we should be trying to push the boundaries of our understanding. Now, that being said, was I surprised? Absolutely, I was surprised. Absolutely. I was excited. And, again, textbooks are written based on what we understand at a given point in time. But as soon as they're written, they become outdated, don't they?
Yes.
And so, this is kind of a textbook defying discovery. and one that will require textbooks to be updated in the future. But that's what we should be doing as scientists. And certainly when we're working in extreme environments where we have this essentially alien life form, we're not talking about microorganisms like E. coli or yeast that run-of-the-mill organisms that a lot of researchers study. Nobody had ever isolated this organism before or anything really remotely close to it. So we shouldn't expect to fully understand what these cells are capable of.
Right. I love that. It's one of my favorite things about science. It saddens me that it's been a little weaponized against us scientists, but that room for questioning and possibility, we leave that there because we know that we don't know everything and that we are going to constantly be surprised by what we don't know. But it's hard to explain that to other people and be like, but science changes, yes, but it's not that we were wrong. It's that we didn't know, we were not quite there yet. Like there's more information we have to have. So I love this research that, you just kind of went, I'm going to try anything. I love that you sound like, that you're open-minded about what the possibilities are, that you're not just going, okay, it can only be this one thing and we're going to leave it at that. So go ahead.
I think that the phrase might be never stop exploring.
Yes.
In a sense, that's what scientists are. And, that's what we do best is creative exploration. It's not unguided. We use scientific principles to guide our exploration, but we're seeking new knowledge. Not just new knowledge for the sake of new knowledge, but because it might be applicable to solving some greater challenge that humanity faces. And NASA is the leader in funding that kind of guided creative research.
Yeah. Not going to get into that too much. All right, I'm going to welcome in some people one more time here. And let's see, we have more people from California, south of France. And I saw Iowa. Okay, cool. Very nice. We are talking about a microbe that was discovered at Yellowstone National Park that breathes both oxygen and sulfur somewhat simultaneously. I'm not saying that they're doing it at the same time, but let's talk a little bit. Okay, so if these microbes can adapt their metabolism with this sort of flexibility, do you think that other organisms could do the same? Could we look for more that we haven't noticed yet? We were talking beforehand about how like you find one and that's an anomaly, but if you find two, there's got to be more than that, because once it happens at least twice, you're like, all right, well, we can find them everywhere now. So where are we at this point?
Well, I think we're at the tip of the iceberg, and there's no doubt in my mind that this happens more readily than just this singular example. And there are some clues to that in the literature. For example, cancer cells, when there's plenty of oxygen around, they'll continue to ferment in a kind of an anaerobic form of carbon metabolism when there's oxygen around. Now, the question is why do they do that? Is it actually beneficial to them? Is that a selectable trait? But those are eukaryotic cells, which are far more complex than the simple organisms that we grow. And so one of the things I'll just point out, I mentioned earlier the redox tower, and that redox tower, not to get into specifics, goes from something like plus 800 millivolts down to say minus 500 millivolts. And oxygen is right near the top of that redox tower, and elemental sulfur is right in the middle. And there's a whole bunch of other possible ways of breathing in between elemental sulfur and oxygen. And I wouldn't be one bit surprised if we don't start to find evidence for microbes that can breathe, say, oxygen and ferric iron at the same time, or oxygen and nitrate at the same time, and do so in a beneficial way. That's the key. It's in a beneficial way to the cell.
I like this idea. So kind of getting a little bit more bigger picture here, what does this tell us about life on early Earth when the oxygen levels were still changing? You mentioned that, we didn't used to have oxygen in our atmosphere. Thank you, cyanobacteria. So what does this tell us about life on early Earth, the possibilities even?
Yeah, I love that. Thank you, cyanobacteria. Without them, you and I wouldn't be here talking about these microbes because higher forms of life would have never been able to evolve. And um, it so early Earth, from the origin of life, whether it be 3.8 billion years ago, 4 billion years ago, up until right around 2.5 billion years, there wasn't free oxygen, or if there was very, very little, orders of magnitude less than what we see in the atmosphere today. And so the life that evolved under those conditions didn't have to worry about oxygen.
Mm-hmm.
And right around 2.5 billion years ago, though, cyanobacteria had evolved, probably somewhere around 2.8 billion years ago. It started to make enough oxygen that it started to creep into environments. And one of my colleagues, Ariel Ambar at Arizona State University, coined these whiffs. There was whiffs of oxygen that were infiltrating different ecosystems. And well, those microbes had to respond. And so while we're so dependent on oxygen, it turns out oxygen is one of the most toxic molecules on the planet. Okay, and so that's true for us. That's true for microbes. It was certainly true for a microbe at 2.5 billion years ago that had never seen it before. And so what that meant is some microbes had to retreat into environments where there was no oxygen.
Mm-hmm.
Some microbes just developed detoxification strategies for oxygen. Others said, well, hey, for reasons I outlined before, maybe I should learn how to take advantage of this oxygen. Now, if that was your strategy, you wouldn't want to go full in on oxygen because remember, it was just these whiffs. It wasn't omnipresent, and it was temporal. And so maybe there would be a molecule of oxygen that came into that floated past your cell wall once every day. Well, if that's the case, then you better have some other mechanism to generate energy. And what I envision in my mind is that these cells were happily growing with hydrogen and elemental sulfur, and a molecule of oxygen would creep by every once in a while. And they said, oh, oop, I'm going to grab that, take advantage of it. And that just kept getting selected for because that amount of oxygen kept increasing systematically over time. And he'd say, okay, well, how is this metabolism still selected for today
Mm-hmm.
in these hot springs where you have 21% oxygen in the atmosphere? Well, remember, there's a lot of evidence that life originated in a high temperature environment, like a hot spring. And hot springs have been present on Earth since its formation and ever since, and they still exist today. That organism probably never left its hydrothermal environment. And remember, the solubility of oxygen inversely proportional to temperature. So whatever concentration oxygen you have in the atmosphere, what's in solution is going to be far lower. And so those organisms, essentially are living in an environment that's not terribly different than probably what it looked like, say, 2.5 billion years ago.
That is really, I love this. I love this because, I have talked with, our Drake Award winners this year were two scientists who talk about the possible origins of life. One talking about, hot springs and pools of hot liquid, and one talking about hydrothermal vents under the ocean. So, we do have two possible hot liquid environments where life could have started. And then, I've been talking to a scientist who's looking at Titan and the possibility that there's enough material there that they could use fermentation as a way of creating energy, and that I'm learning a lot about microbiology this year, I have to say, and I'm not disappointed. It's actually kind of fun. So it's just really fascinating to me that when we get down to these to microbes, yes, I know we're SETI and we're supposed to be looking for extraterrestrial intelligence, but I really think this is where you start. You start with the basics, and that's where we're at. And I love this. So, thinking about these microbes, how can we apply this? How does it help us think about life on, say, other worlds like Mars, Europa, and Enceladus, places where we think either has been, in the case of Mars, where there was water, or Europa and Enceladus, even Titan, where there is liquid and it does seem to be some sort of heat mechanism that can give us that energy that we need. How do the microbes like this help us think about that?
I'd simply say this, that, where there's water, life will find a way. And this is a challenge to your audience, to members of your audience. Please come up with an environment where there's liquid water and we cannot find evidence for life. And that's the challenge. And that's on Earth. And so then I'll just extend that logic. Then why wouldn't that be the case on any planet where we can find liquid water? Now, Mars is a challenge because right now, today, present day Mars, there's not a whole lot of liquid water on the surface of Mars. But that's not the case for its history, its entire history. And so there was water on Mars. There were hydrothermal vents, or at least hot springs, on Mars. And how do we know that? We can find minerals on Mars that only form under hydrothermal conditions. Mm-hmm. They would have been slightly acidic, similar to maybe the roadside west spring that we just discussed. And so again, I just want to reiterate, where there's water, life finds a way. And this is just another example of life adapting to its chemical environment to compete and to persist under those conditions. And people ask me all the time, do I think that there's life on Mars, or could there have been life on Mars? And absolutely, I do. I see no reason there shouldn't be. Now, will there be? Will we be able to detect it? That's a different question. What about Europa? Europa presents us another set of problems, but again, there's water, and I think microbes will find a way. We find microbes living underneath ice sheets that are kilometers thick, mm-hmm. Where you find liquid water. Why wouldn't there be something similar on the inner wall of that ice shell of Europa, and similar for Enceladus?
Sample return missions, everybody. Sample return missions. Ask for sample return missions. Okay, I'm going to take a couple of audience questions since we're kind of getting to the end of the time here. Let's follow on this. Terrence is asking, could microbes remain dormant within rocks on Mars, with the small Martian atmosphere that is there? Could we maybe rehydrate? Is that a possibility? Is that something that happens here on Earth?
Well, I just went over this example in my class. I teach an astrobiology class, undergraduate class, and I brought in a piece of granite countertop from a local countertop dealer, and essentially I asked the class whether or not they think life exists in that countertop. This is the countertop that people use in their kitchens, and the answer is yes. We proved that. I had a student that proved that. That was her testing ground before we went and started working on rocks that were much more difficult to get access to. So precious rocks. Microbes live in rocks. That's the first thing. That's the first part of the answer to your question. The second part of the answer to your question is, I don't even think we need to imagine dormant cells within these rocks. You don't have to go very deep into the subsurface of Mars where you can start finding water ice. You probably wouldn't have to go too much further than that to find liquid water. And microbes are amazing. They can persist, a dormant state or not, even under fairly cold conditions, not freezing conditions. You need it to be liquid water. So yes, I think absolutely cells could remain dormant within rocks on Mars. And I think we could maybe even take it a step further and say that we might as well expect them to be active.
Oh, I like this. Okay, now I'm really hyped for a sample return mission. Okay. One other one. Well, I do want to address Shelley's question just because I'm kind of amused. Shelley wants to know if the sulfur makes it smell like burnt wires.
Yeah. So the smell it's rotten egg smell. that's the smell. And or if you're following a car too closely in front of you and that rotten egg smell, that's sulfur dioxide. But when it hits your nose and the liquid, the moisture in your nose, it disproportionates and makes sulfide and sulfate. And so it's that sulfide smell that gives it that smell. And so burnt wires, let's not go out and burn any wires anytime soon, but that is the correct smell. Yes.
Fantastic. It's true. The few times that I've gotten to get near Sulphur Hot Springs, it is a very pungent area. You do get a little desensitized to it, but not much. We're not built for that. That is definitely one of those warning systems of, this is not a good place for you. You need to not be here.
It is, and I tell my graduate students, it's the smell of success. So learn to enjoy that smell, whether you like it or not.
Oh, I like that. That's good. TA is asking, with everything that we've talked about, is this good evidence that any alien life form may be possible as long as it's physically probable?
Yeah, I don't see any reason to go against that statement. Again, what you mean by physically probable, like kind of the aspects of the Drake equation. So sure, as long as we satisfy that, and you've got an environment that has a solvent, or you've got chemical disequilibria to drive energy metabolism and organization, sure, I have no problem with that.
Life finds a way, I think, is the takeaway here today. So, Eric, what's next for you? What is next on the agenda? What are you looking for, more of these microbes? Are you looking for new ones? What's the next steps for you?
Well, we're still working on this same microbe. To ask similar questions to what we asked before, like what have we missed? Is there something more interesting about this organism? And of course there is. One of the things that I've really gotten excited about recently, and we just had our first paper on this accepted. It's not yet in publicly available, but it will be, and free of charge. It's open access in the journal PNAS. But essentially asking the question, in the subsurface of Yellowstone, can you find evidence for life in the aquifers that feed the hydrothermal system in Yellowstone, and B, what fuels that life? And one of the things that we've been really excited about is thinking about the effects of earthquakes, and earthquakes maintaining chemical disequilibrium. And by that I mean, hydrogen plus elemental sulfur, hydrogen plus oxygen. Well, you need something to keep those compounds in disequilibrium, or they'll naturally equilibrate, and there's no energy then under those conditions to generate to sustain life. So how do you maintain that, and how can you maintain that over extended periods of time? What we were able to show is that microbes in the subsurface of the Yellowstone exist. They're fueled by very similar metabolisms as you find in hot springs, and they're stimulated. They respond dynamically to earthquakes. It almost causes you've heard of cyanobacterial blooms, when you have a bunch of fertilizer runoff go into a lake and you relieve some nutrient limitation or energy limitation. Think about it the same way. When an earthquake happens, it's like you dumped a big vat of electron donor or electron acceptor. These cells become very happy. You get a bloom of activity. The earthquake swarm dissipates, and the cells go back to their state, their ground or resting state. So thinking about that intersection between the geosphere and the biosphere, even the hydrosphere, and what that looks like in terms of the habitability of a subsurface system, both on Earth and say on Mars, where we know Mars quakes take place as well.
I want to read this paper. I am really super excited about this. I have, as both an astronomer and a planetary scientist, a geologist, I really love the way that scientific communities are kind of coming together and combining their knowledge. It's no longer sort of like, it's not so siloed. This is Earth, and we're just going to focus on that. This is Mars, and we're just going to focus on that. It's what if we just start combining all of these things and looking at them more, holistically? And it's amazing what we're finding and what we're coming up with. So I love hearing more about combining these different research areas into one topic. So
Yeah, Beth, I'll just iterate that. True discovery happens when we get out of our comfort zone. And so by that, I mean me working with a geologist or a seismologist. We speak very different languages, but as soon as we start talking, right? So we're uncomfortable initially, but as soon as we start talking, we start sharing ideas. True discovery happens, and NASA, just for its history, has promoted that way of interdisciplinary science to the extent possible, and I hope they continue to do that.
me too. Again, preaching to the choir, but absolutely. Well, thank you, Eric. Where can people learn more about your research or follow your work? I don't think you're a social media maven like I am. So is there any place people can specifically check out what you do?
I am not on social media. That's on purpose. The reality is the best way to keep up on what I'm doing is we have a website called geoboidology .com, and you can search for that and it'll come right up, or just search my name. You'll eventually find that website. But we post our papers there. And links to those papers. We also post announcements about job availability, highlights from our lab, so on and so forth. And so again, we have a pretty up to date website that you can go to.
Awesome. I'm going to share that in the comments here, and I will add it to our show notes. So if you want to find that, let me just throw this into the chat. There we go. And so you can check that out and take a look at their research and what they're doing in their lab. And thank you again, Eric. Discoveries like this remind us that life never stops surprising us. As we keep saying, life finds a way. And sometimes the smallest organisms, they have the biggest stories to tell. So thank you again, Eric, for joining me today and taking the time to talk to us.
Absolutely, Beth. And thank you all out there all over the world for joining as well.
So if you enjoyed this conversation, please like it, share it with your fellow science nerds, subscribe on our YouTube channel to keep up with more space science and astrobiology interviews like this one. Join us tomorrow at 1 p.m. Pacific, 4 p.m. Eastern for a special SETI Live with Frank Marchese and Ariel Grykowski to talk about, you've all asked, you've all been bugging, you've all wanted this. We're going to talk about Comet 3I Atlas, what it is, what it isn't, and what we have observed so far. And next week, we once again have 2 SETI Live events. So on Monday, I have the pleasure of introducing our newest SETI Live host, Dr. Moya McTeer. So come learn all about her if you don't know her yet. She's a friend of mine. She's wonderful. We're really excited to have her joining our team. And then on Thursday, Moya gets to do her first interview, and we'll be chatting with a pair of scientists about TRAPPIST-1e and the possibilities of its atmosphere. So stay tuned, everybody. As always, the SETI Institute is a 501c3 nonprofit. Your subs, your bits, your super chats, your stickers, all of these things help support our outreach program. If you want to make a slightly larger donation, you can go to our website and click that Donate Now button, and we will be very, very eternally grateful for all of your support. Also, you can subscribe to our weekly newsletter, Journey, and that will bring all of this news and our SETI Lives straight into your email box once a week. Until next time, everyone, keep looking up and stay curious.